No, I watched it. I liked it. It's pretty cool. I I don't know if you I don't know if it's pronounced Bridgerton or Briggerton. It's kind of hard to tell the way they say it because they're British. But hey, I like period pieces. Hi, hi everyone. Week 3 of Stats and Research 2 here. We are going to continue on with what we've talked about. Like I said, everything kind of builds off of the previous week. So, excuse me, as we've talked a little bit about different variables and then levels of measurement last week, we are going to incorporate those into determining how to best display our data by creating graphs and whatnot. But first, we're actually going to kind of do 2 parts because I think we have a lot of material here. So this first part, we are going to talk about measurements of central dispersion. And we talked about centrality, measures of centrality earlier, central tendency rather, earlier last week, and we're going to shift a little bit to give another type of descriptive statistic to better cover the data we are going to be displaying in those graphs and charts and whatnot. Let's recap just a little bit of what we talked about last week. Categorical levels of measurement include blank and blank. Remember, categorical, we're talking about groups, we're talking about people, places, things, so to speak. Categorical is going to be nominal and ordinal. We can see it outlined in question 3. Difference being that ordinal you can rank and order them, put them in a logical order. Continuous levels of measurement include ratio and interval. Ratio is going to be used more commonly, but interval is very similar to ratio. There's just some differences with absolute zero and things like that where the actual values begin. Ratio is going to be your very standard numeric frequencies of whatever, crimes, people locked up, any other scenario that could play a number of arrests, number of shootings, any other scenario that could play into criminal justice research. One example here, in a study of people incarcerated in prison, the variable offense type captures the crime each inmate is convicted on. How could this variable be coded as either nominal or ordinal? So this is a categorical variable offense type, but depending on how it is actually described and how it is measured, then it can be either nominal or ordinal. An example, nominal, if we're just looking at groupings, we could say ordinance violation, people usually aren't incarcerated on that, but ordinance violation, misdemeanor, or felony. Also, they're mainly incarcerated in prison on felonies, but those are 3 different types. And you can kind of place them in order of severity, but not exactly. So that could be one way you could do it. Or interpersonal violence, property damage. Those could be 2 different groupings of different types of offense. Is one more severe than the other? Generally, we think interpersonal violence is more severe than property damage, but it depends. Is a fight where somebody gets a bloody nose more serious than a Bernie Madoff scheme where somebody loses millions of dollars and there's no actual physical interaction between 2 people, but it's a property crime or financial crime? So it is arguable. Or no, if we were to look at the offense type based on actual levels of felony, perhaps, murder, X, 1, 2, 3, 4, going down in severity, that could be a way that we could rank them. The 3 primary measures of central tendency, also known as the averages, we look at mean, median, and mode. The blank cannot be used to measure categorical variables. So out of those 3, the answer would be the mean. We need to have a numeric value in order to, it needs to be continuous, quantitative. We need to have a numeric value in order to determine the mean, which is the arithmetic average. We do not get that with categorical variables. So we're going to look at measures of central dispersion, and we're going to see besides the average, besides the value that's the average, what else do we need to say about a group of values to better describe it? And we want to look at variability for an important reason. But let's just say we have three different groupings we have 15 values placed into three groups of 5. And we ask ourselves, what's the mean? So what is the arithmetic average of these 5 different values? 7, 6, 3, 3, 1, and so on. We notice that the mean of 4 is actually the same for all three groupings. However, we can see quite a difference in the actual values. There's a difference in the range, which we'll talk about, and a standard deviation as well, most likely. The first example goes from 7 to 4. And then our other example at the bottom, each one is 4. So if each value is the same, then obviously that will be the mean. But we also get the mean of that value possibly in a grouping of values that has a very wide range, has a very large range of 6 in this situation, going all the way from 1 to 7. So it's very important to have another qualifying descriptive data attached to the mean where we can better describe the variability of those values. We need something to go along with this mean of 4 and say, yes, the mean is 4, the average of these values is this, but the values themselves are spread out in this way. They vary in this way. So that we can differentiate between this group of all 4s and this group of 7, 6, 3, 3, and 1. Because there is quite a difference if we are to look at those groupings as a whole. So this is what I just explained. They can be very different values within that group of value, that set of values. So we need to figure out how we can measure that. So the 3 most common measures of variability or dispersion that we're going to focus on: range, standard deviation, and variance. Standard deviation is the one that's talked about the most. We'll go over these a little bit as well, and you'll need to be quizzed on them and tested on them just so you understand really where they fall in statistics. But standard deviation is reported quite often in statistics, usually along with the mean. So we usually report these together. The mean, not always the mean, but usually the mean, and then the measure of variability, standard deviation usually. Because if we don't have a mean to go along with it, we can't report how much these values vary if we don't have a point of reference being the mean. So if we have a standard deviation of 1.5, meaning that a certain number of values are 1.5 higher than the mean or lower than the mean, that doesn't really matter if we don't also give the audience the mean. We don't also let them know what that average is. Everyone with me? You are? Okay, good. The range is going to be the easiest measure of central dispersion to calculate. You just take the highest value and subtract the lowest value from that. So that example I gave, we had 5 values that range from 1 to 7 or 7 to 1, however you look at it. So that would be a range of 6. H minus L, H representing the highest score, L representing the lowest score. You can also look at another way to write this: H subset max, subscore max, minus X min. That just refers to whenever you see X as itself and then with some other things attached to it, That just represents the value in general. So we're looking at the maximum x value minus the minimum x value. So another way of saying the highest value minus less the lowest value. So very easy to calculate, not exactly useful, especially if there are outliers involved, like the outliers we talked about with in situations where you want to use the median. If we have outliers, then that's going to give us a very big range, and that might not necessarily be accurate to 99% of the values. We just have one outlier. If you think back last week, maybe week 1, I don't remember, the example I gave of numbers, we had all the way from 1 to 500, I think, but pretty much everything was less than 100. So we'd have a range of 499, but that's really influenced by that outlier of 500. So it can be somewhat misleading. Here's a formula for the computation for standard deviation. So your standard deviation is the average of the amount of variability in a set of scores. You'll have a mean that you come up with from this set of scores. And then it's interesting to see how far away each one of those values is from the mean. However, you can't really do anything with each individual number, especially when you get into large data sets where you're using more than 100 cases, more than 100 values. So what you want to do is you want to see, on average, how far away are these values from that average value, that mean, most likely. And here's the formula that you will use. You want to become familiar with that with the quiz, for the quizzes and the test, but more just knowledgeable about what each means. So like I said, this is standard deviation. We have a couple of different, I talked about the x already. What we call x bar just is what we use to represent the mean. So the mean of all scores. You'll see sigma sometimes, meaning just it indicates that you'll want to be looking for the sum of whatever follows sigma. So we can see within this square root formula, under this, within the square root element of the formula, sigma of x minus x bar, and then that's squared. So, and it also includes n, which is the sample size. A couple things to remember about these. Excuse me. So like I said, the average distance from the mean. You need to have that mean in place before you start to formulate the standard deviation. If you remember, x bar was in there in the formula, that represents the mean. So the larger the standard deviation you have, the more spread out the values are. Okay, so if there is a standard deviation of 0, there's no variability among the scores. That third set in the example I gave earlier of all 4s, that would be a standard deviation of 0. And as I referenced before, that standard deviation is also, I referenced it in terms of the range, but the standard deviation is also sensitive to extreme scores or outliers. As I said, the larger the standard deviation, greater variability. Smaller standard deviation means there's less dispersion or variability. The general concept, and I was going to put a diagram up here, but I forgot to do that. This one of the fundamental concepts of standard deviation in the normal curve. The normal curve, we'll talk about that in a couple weeks, I think, possibly. But that's just the bell curve that we talk about, where you have this natural peak of values, curved peak, I guess, of values right along the middle, right along the mean. And that's also why it is the mean, is because you have so many values there. If you have a group of 100 people, you're going to tend to get most of your values right in the middle, close to that mean, which is also why it is the mean, is because you have so many values that are close to it. But generally speaking, about 2/3 of your values are going to be within one standard deviation above the mean and one standard deviation below the mean. So that normal bell that we see, maybe I'll do some post-production in here, and this thing we see, I'll do it over here. This bell we see right in the middle is going to be the mean, and that bell is just happens to be where the values are. That's not on the y-axis right at the 0 necessarily, but so there will be 2/3 will fall within one standard deviation ahead and one standard deviation below. Now that's for a normal bell curve. If we have something that's really skewed and we have something like that, it's not going to apply the same way. We're not going to go through this, but I want to show you how, and this may be something you have to do. That may be something you have to do on an exam, which I'll need to figure out with online exam taking exactly. But you'll be given elements of that formula that we talked about with standard deviation, and you'll have to input them. So if we take an example of just a very small n, an n of 6, 6 different states we're looking at here, death row inmates by state. We see, what do we have? Louisiana, Mississippi, Nevada, Arizona, Pennsylvania, Oklahoma. I believe that's the correct abbreviations. And we see a range of different inmates currently on death row, I guess. So before we get the standard deviation, we would have to get the mean first, which is located at the bottom left. We see sigma x, which is the sum of all the values, so the sum of all the x is divided by the n, which is the sample size. So it's the sum of 84, 50, 81, 122, 190, divided by 6 in this case. So people are familiar with what the mean is, the arithmetic average. And then we need that to enter that into all these other values. And we're not going to go through all of this, but you can see in the third column, to come up with x minus x bar, we just less the mean from all of these values, 84 minus. And then it might come out that we get some negative values, but then we square them ultimately. Then at the bottom of that, so the far right bottom corner, we see that we sum all those values, and then we just fill in the rest of the formula that I showed earlier. So I believe that's correct off the top of my head. I actually didn't recheck these values, but I believe that to be correct if it did follow everything. And also I don't have anything mapped out for this, but what we would do, I'll try to do some calculations in my head right now, but 43.18 is the standard deviation. So a mean of 95.83. We should know that there are 2/3 of values. 2/3 of the values are within one standard deviation above and one standard deviation below 95.83. So let's just say 96 and 43. We'll say it's 96 and 43. So one standard deviation above would be 139, I believe. And then below would be 52, we'll say. So 52 to 136.9, I think I said, somewhere around that. So there are six values, so 4 of them should fall within that range. And just kind of putting them in order right now, it looks like that would be 50 through 122 in this case. Those would be the values that fall within those standard deviations. And that seems like it makes sense, actually. So, that's a very small sample of only 6, so you wouldn't really, this isn't as valuable, but it does usually pan out that way. And I'm not sure off the top of my head if that all works exactly, but it seems like it's pretty close just from running through those in my head. Okay, so I'm actually going to do a second part of this as well, where we look at some of the graphs and charts, but that's a good explanation of these measures of central dispersion, measures of variability. They give us an additional qualifier to the descriptive statistics that we talked about. They kind of further explain the average that we came up with of this data set to explain where the different values are and help us understand if this grouping of values, even though we have this mean, if everything is directly on that mean or very close to it, or if things are spread out a lot, because that gives us two very different understandings if we're talking about scores, if we're talking about weight of individuals to determine if there's an issue with obesity or something, which I know isn't a criminal justice issue, but you have some very different makeups of a group depending on the variability. Okay, so they're important to understand when we are describing the data, those data that we have. So we're going to break here. I'm going to end this video here, and then we're going to have the next video. You can watch it right after this. YouTube does a thing, I think, where it does up next, play whatever's up next. So you guys know, you get it. So I'll see people then. So yeah, Bridgerton, however you say it. I thought it was really great. Like I said, I like period pieces. Have filled the void that Downton Abbey left for me in my soul. So yeah, I like it a lot.